Noche cósmica.
Imagine for a moment that you could travel at the speed of light itself, that impossible, unreachable velocity that only photons know, and imagine you pointed yourself toward the center of our Milky Way galaxy. You would travel for 26,000 years. 26,000 years of unbroken journeying through the dark, moving at the fastest speed the universe permits, and you would arrive at a place that, by human measure, is almost impossibly far away. Yet it sits there, it has always sat there. Waiting in the profound quiet of the galactic core is something that has shaped the entire spiral of our galaxy for billions of years, and most of us will never see it, never hear it, never feel its presence except as mathematics on a page. What draws everything in our cosmic neighborhood into its orbit is also the thing that asks us nothing in return. This is a journey inward, not outward. Most of astronomy asks us to look up at brightness, to find our home among the stars we can name and trace. But the heart of the Milky Way lies in a direction that the dust itself obscures, a region so crowded with ancient starlight and cosmic smoke that visible light cannot reach us there. To find what rests at the center requires different tools, different ways of listening. It requires patience, the kind that measures time not in human lifetimes, but in decades of quiet observation. The object we're traveling toward has a name that sounds almost like a designation, a catalog entry. Sagittarius A. The asterisk at the end carries a reason, a story, and the name itself points not to something newly discovered or sudden, but to something that revealed itself slowly, reluctantly, through the dedicated work of people who spent their nights pointing radio telescopes at one small patch of the sky, again and again, year after year, until the signal they were hearing began to tell them something extraordinary. If you find yourself drawn to the mysteries of cosmic scale, to the calm that comes from understanding that the vast architecture of our galaxy turns around a quiet center, then please subscribe for our full journey through the most relaxing facts about Sagittarius A. Stories that trade alarm for wonder, that transform the heart of our galaxy from something fearful into something almost serene. But before we arrive at that distant place, before we step into the full light of what we now know, it helps to descend slowly, to let your mind drift outward from where you are now, past the familiar dome of night sky, past the sun's small sphere of influence, past the orbiting ice and rock at the solar system's edge. The stars themselves begin to blur together as you travel, their individual light merging into the faint river of the Milky Way, that cloudy band that ancient peoples watched and wondered about long before we knew what it was. You're moving deeper into that river now, through regions where the air grows thick with stellar nurseries, where young stars ignite in clouds of gas, where the density of light increases as if you're sinking toward a source. And there, at the absolute center, invisible to our eyes because the dust is too thick, sits a region of absolute stillness. Not because nothing is happening there, quite the opposite, but because what is happening is so fundamental, so gravitationally dominant, that everything else orbits in patterns of such mathematical grace that from a distance, from where we observe it across those 26,000 light-years, it appears almost tranquil. The stars around it move in elegant, patient paths. Vast clouds of gas orbit slowly, taking millions of years to complete a single revolution, and at the very center of it all, compressed into a space smaller than our solar system, sits approximately 4.3 million times the mass of our Sun. This is Sagittarius A, a supermassive black hole so enormous that it makes the stars we see in our nighttime sky seem like grains of sand scattered across a beach, yet so distant from us that its gravity touches us only through the indirect choreography of the galactic dance. What makes this place worth our attention isn't danger or spectacle, It isn't the roaring maelstrom that Hollywood imagines when people hear the words black hole. What makes Sagittarius A worth drifting toward in the quiet of the evening, worth contemplating as you rest, is something almost the opposite. It is a place of profound stillness. It is a master of gravity so complete that it asks nothing of the universe except that everything fall obediently into its patterns. And in return, it demands so little from the material around it that by the standards of such objects elsewhere in the cosmos, it remains almost dormant, almost content. This is the story of how we found it, how we learned to see the invisible, how we listened with our entire planet acting as a single ear and heard the whisper of the galaxy's heartbeat reflected in starlight bent around darkness, and how that discovery, rather than diminishing our peace, instead offered us a new kind of calm, the calm that comes from understanding exactly where we are in the machinery of the cosmos, and how that machinery, though vast beyond measure, turns around a place of almost hypnotic tranquility. There is something profoundly settling about knowing where you are in the vastness. 26,000 light-years from here, at the very heart of the Milky Way, the spiral arms we belong to, there exists a place so still, so perfectly balanced in its darkness, that it has ordered the motion of 200 billion stars around itself for the entire age of galaxies. That center holds a quiet. If you have ever found peace in scale itself, in the realization that your small corner of worry sits within something so much larger and older and calmer than you, then perhaps the journey to that galactic heart is one worth taking in the soft hours before sleep. The heart of everything we see in the night sky beats in a rhythm we can measure, almost feel, as we learn to listen. For those of you drawn to these kinds of voyages, to the places where immensity becomes intimate, where the largest mysteries resolve into gentle facts, you might want to journey with us regularly through the cosmos and the deep patterns underlying it all. Consider joining this exploration, where we venture together into the true architecture of the Milky Way, learning how to read the universe not as a place of chaos or threat, but as a cathedral of order, where even the most extreme physics unfolds with an almost mathematical poetry. There will be many more nights like this one ahead, many more descents toward understanding. Now, in the darkness of that galactic center, something extraordinary rests. Most of us have heard the term black hole, and most of us have felt a small instinctive pull of fear at the phrase, as though the universe harbors a cosmic drain, a place where things go to disappear. But the reality is far more subtle, far more calm. What sits at the heart of our galaxy is not a drain or a tear in space, but rather the gentlest possible expression of gravity taken to its extreme conclusion. A supermassive black hole is simply a place where gravity has become so profound, so patient and thorough, that it has sculpted the very fabric of space and time itself into a shape we have never encountered in our smaller, gentler earthly experience. Now, before we move deeper into the story of how this object came to be known and studied, it helps to sit with what it actually is, and perhaps the best place to start is to say this. A supermassive black hole is not a vacuum cleaner. It is not a cosmic drain that indiscriminately swallows everything around it. Instead, imagine it as an extraordinarily dense point in space, a place where gravity has become so concentrated, so fully present, that it has fundamentally reshaped the fabric of reality itself. At its heart lies something called the event horizon. Think of this not as a wall or a barrier you might touch, but rather as a mathematical boundary, a point of no return. Beyond that invisible line, the pull of gravity becomes so overwhelming that even light, that fastest of all things, cannot escape once it crosses that threshold. But here is what creates a strange and almost meditative quality to this idea. If you were somehow far enough away, watching from a safe distance, you would see almost nothing happening. no violent swirling, no dramatic consumption. Instead, what you would witness is a kind of infinite stillness. Objects approaching that boundary would appear to slow down, to move more and more slowly, their light stretching and dimming as they approached, eventually fading into darkness. Time itself, from your distant vantage point, would seem to stretch and lengthen in ways almost poetic. Consider gravity as you know it, the familiar force that keeps your feet on the ground, that holds the moon in orbit around the Earth. That same gravity exists everywhere. It is not separate from us. It is woven into the structure of the cosmos. What a black hole represents is not some alien violation of the universe's rules, but rather the ultimate fulfillment of them. It is gravity, taken to its most complete and intense expression. Take all the mass of a star, compress it down to an infinitely small point, and you create a singularity, a place where density becomes infinite and the equations of gravity reach toward infinity as well. This is not destruction. This is a kind of perfection, a place where one of the universe's fundamental forces is most purely itself. And yet, here is the fascinating paradox. A supermassive black hole like Sagittarius A is, in many ways, the calmest object at the heart of a galaxy. Surrounding it, yes, there can be turbulent activity, hot gas, spiraling clouds, occasional flares. But the black hole itself, that central point, that event horizon, it is utterly still. It does not pulse. It does not change. It simply exists, holding its shape, maintaining the invisible geometry of gravity that keeps billions of stars in orbit around it. In this way, a black hole becomes a kind of cosmic anchor, a place of profound quietude at the very center of everything. Many people, when they first hear the term black hole, feel a whisper of unease. Something about the idea of a place from which nothing escapes feels unsettling. But consider this. You are already within a gravity well. The Earth's gravity holds you here. The Sun's gravity holds the Earth. Sagittarius A's gravity, unimaginably powerful though it is, operates on the same principles, following the same elegant laws. It is not malevolent. It is not hungry. It is simply present, simply being what it is, a concentration of mass and the gravity that inevitably follows. And at 26,000 light-years away, it exerts no pull on you whatsoever. It exists in its distant stillness, indifferent, eternal, and in that indifference lies a kind of peace. The universe unfolds according to laws that are predictable, beautiful, and utterly impersonal. We are not in danger from it. We are merely aware of it, and in that awareness, we touch something profound about the nature of existence itself. In the early 1970s, before satellites filled the sky, and before the digital age made instantaneous observation commonplace, astronomers still worked much as they had for decades, patiently, methodically, tuning their instruments to the quiet whisper of radio waves traveling across space. The radio frequencies that carry no visible light, that pass through dust clouds where optical telescopes simply see a murky curtain. These frequencies held secrets that patient listeners could extract. And in the direction of the Sagittarius constellation, in that dusty, crowded region of sky toward the galactic center, something extraordinary was beginning to be noticed. The Sagittarius radio source wasn't immediately recognized as anything particularly special. It emerged from the hum of background noise as what radio astronomers simply began calling Sagittarius A designation as plain and methodical as the work itself. In those days before computerized analysis, the discovery of a new radio source was almost a routine occurrence. The sky was full of them, chattering quietly at frequencies the human ear could never hear. Radio galaxies, remnants of stellar explosions, distant quasars and active galactic nuclei, each one a whisper in the cosmic dark, each one requiring careful study to understand its nature. But there was something about this particular source in Sagittarius that would eventually set it apart. What made the detective work of those early years so quietly compelling was its fundamental simplicity. Radio astronomers would point their dishes at these sources night after night, week after week, measuring the strength of the signals, noting how they changed or remained steady, plotting the data by hand in many cases, looking for patterns the way a naturalist might observe the habits of a creature in the forest. There was no urgency to it, no assumption of breakthrough, just the steady accumulation of observation, the building of a portrait through patient measurement. The work required a kind of intellectual humility, a willingness to let the data speak on its own timeline rather than rush toward conclusions. The radio source in Sagittarius was peculiar in a quiet way. It was compact, not sprawling across enormous regions of sky like some of the other radio sources they had catalogued, but concentrated, dense in its emission. It flickered occasionally, its brightness varying on timescales that spoke of something small, something energetic, something constantly churning, and it was bright, far brighter than you might expect from an ordinary star or even from a supernova remnant. There was a mystery embedded in those radio measurements, though it would take decades for the full shape of that mystery to become clear. The work of radio astronomy in that era had a particular character to it, a blend of patient engineering and intellectual curiosity. The radio dishes themselves were marvels of mechanical precision, great curved surfaces of metal that could be pointed toward any region of sky, that could be tuned to detect the faintest whispers of radiation from the distant cosmos. But they required constant maintenance, constant adjustment. The data came slowly, through techniques that were sophisticated by the standards of the time, but would seem almost primitive by modern standards. Yet there was something meditative about this work, something that required a kind of focused attention, a willingness to spend hours, nights, months, pursuing an observation that might yield only a small piece of a larger puzzle. The scientists involved in these early observations were not hunting for a black hole, because at that time, black holes remained largely theoretical. They existed in the mathematics of general relativity, elegant and strange, but they had never been directly observed. The prevailing assumption in astronomy was that black holes, if they existed at all, would be rare, perhaps even non-existent in the real universe. So the Sagittarius radio source was approached without preconception, without the assumption that something extraordinary lay at the galaxy's heart. It was simply a puzzle waiting to be solved, and the only way to solve it was through more observation, more measurement, more accumulation of data. The detective work itself unfolded slowly, without drama. New measurements were added to old measurements. Radio astronomers at different observatories compared their results, cross-checked their findings, looked for consistency. The source remained active, remained bright, remained mysterious. What was producing this steady, intense emission? Was it a single object or multiple objects? Where exactly was it located within the Sagittarius region? How far away might it be? These questions drove further observation, further refinement of technique. Consider what this kind of astronomical detective work actually entails. A radio astronomer points a telescope at a location in the sky. Light waves, radio waves, gravitational waves, these things arrive at the surface of the telescope, whether we're ready to detect them or not. The task is to isolate the signal from the noise, to measure its intensity, its frequency, its polarization, its variations over time. And then the astronomer records these measurements, analyzes them, and waits. Waits for patterns to emerge, waits for clarity, waits, sometimes for years or decades, until the accumulated weight of evidence finally reveals what the cosmos has been trying to tell us all along. By the mid-1970s, the Sagittarius radio source had become increasingly well documented. increasingly mysterious. Other astronomers, hearing of these observations, began turning their own equipment toward the region, adding their own measurements to the growing archive. A picture was slowly crystallizing, becoming more detailed, though its meaning remained obscure. There was something in the heart of our galaxy, something active and energetic, something that radio waves could detect, even though visible light could not penetrate the dust that shrouded it. The detective work was not yet solved. It was only beginning. Once that radio source had been detected, the astronomers faced a very practical question, the kind that might seem small but carries its own quiet importance. What should they call it? The convention in astronomy, particularly for radio sources, was to name them after the constellation where they appeared, followed by a letter that indicated their brightness or position within that region. So this object, sitting in the constellation Sagittarius, became known as Sagittarius A. But as more sources were catalogued in that same region of sky, as the radio surveys grew more detailed and more precise, astronomers realized they needed to distinguish between them, and so they added letters: Sagittarius A, Sagittarius B, Sagittarius C, each one a separate voice in the radio static. And then, for reasons both practical and perhaps a little poetic, someone decided that the brightest of these sources, the one at the very heart of the galactic center, would be given a special designation, an asterisk. Sagittarius A star, just that small symbol, almost humble in its simplicity, marking something that would eventually reveal itself to be extraordinary. For many years, though, no one quite knew what Sagittarius A semplals. It was simply there, a persistent whisper of radio waves coming from a location that seemed, by all optical measurements, to be essentially empty. Telescopes that looked in visible light saw nothing remarkable at those coordinates. But radio telescopes, which listened to the universe in a completely different way, heard something unmistakably present. There was matter there, something, emitting radiation at wavelengths that human eyes could never perceive. The astronomers who studied it in those early decades, the 1970s, the 1980s, developed a kind of patient curiosity about it. What was this invisible thing? Was it a star? Was it a collection of stars? The radio signals were concentrated, compact, but the resolution of those early instruments wasn't fine enough to say exactly what they were looking at. And then, slowly, methodically, a different approach began to yield results. Instead of trying to photograph Sagittarius A directly, astronomers began to watch the things around it. They looked for stars whose orbits might reveal the presence of something massive at the center, the way planets orbiting the sun betray its position through their motion. This required extraordinary patience. Observations had to be made night after night, year after year, with instruments that grew more sensitive and more precise as technology advanced. The astronomers were essentially watching a cosmic dance, waiting to see if any of the stars in that crowded region near the galactic core showed the telltale wobble or acceleration that would indicate they were being pulled by something immensely heavy, and gradually, unmistakably, they began to see it. Certain stars moved in ways that couldn't be explained by the gravity of nearby visible matter alone. Their orbits curved in patterns that suggested an invisible anchor. Something was there, pulling them, holding them, keeping them in tight, hurried paths. The more carefully they measured, the more the evidence accumulated in one direction. Sagittarius A, this mysterious radio source that produced no visible light, had to be extraordinarily massive. Not massive like a star, not massive like 1,000 stars, but massive in a way that challenged the mind to hold the number steady. The mathematics began to whisper a possibility that many astronomers found almost difficult to accept. What if at the center of our galaxy sat not merely a compact object, but a supermassive black hole? What if that asterisk in the name marked not just a bright radio source, but a place where gravity had drawn the boundary between the knowable and the unknowable. It was a hypothesis that gained strength gradually, not through a single dramatic announcement or a single perfect observation, but through years of convergent evidence, each measurement adding another thread to a tapestry that grew too coherent to ignore. The discovery, if you could call it that, for it was less a sudden revelation than a slow unveiling, changed how astronomers understood the architecture of galaxies. Sagittarius A became more than a catalogue entry. It became a symbol of something hidden at the heart of our own cosmic home, something that had always been there, quietly anchoring the billions of stars that spiral around it in their patient orbits. And as observations continued to improve, as technology developed the ability to peer closer and listen more carefully, that asterisk seemed to shine a little brighter, marking not an empty point on a star chart, but the location of the most extraordinary object within 26,000 light-years of Earth. A place of such compressed gravity, such absolute stillness, at the center of all that galactic motion, that it would eventually become possible to see it, to actually perceive, for the first time in human history, the shadow of a black hole itself. Before there were radio dishes listening across continents, before the first photograph of that dark center was captured by machines, human beings were already watching the region where Sagittarius A now hides in silence. This may seem like an obvious truth. After all, the stars have always been there, but the deeper resonance is something quieter. For thousands of years, cultures across the world oriented themselves toward this particular patch of the night sky, not knowing what lay at its heart, drawn by something that felt significant, something that felt like a gathering place of the cosmos itself. The constellation Sagittarius has been recognized by humans since antiquity, its pattern emerging each year as autumn turns toward winter in the northern hemisphere. The archer, the centaur, the hunter, different cultures gave it different names and different meanings, but the shape remained consistent. A figure drawing a bow, or sometimes depicted as half horse, half human, aiming something precious outward toward infinity. There is a peculiar comfort in observing that the night sky itself feels somehow denser in this direction, somehow thicker with stars, as though we were gazing not outward but inward, toward the spiral's heart. The ancient Babylonians knew this region well. They called it part of their celestial pathways, incorporating it into their mathematical astronomy as they tracked the wandering planets against the fixed backdrop of stars. What they could not have known, looking upward with nothing more than the naked eye, was that they were gazing toward a cosmic furnace so dense that light itself could not escape from beyond a certain threshold. Their eyes, patient and careful, were aimed at one of the most profound mysteries of creation, and the mystery was returned only as quiet starlight and the faint dust lanes that obscure the view. How strange it is that our ancestors stared at the very place that would eventually become the focal point of a centuries-long scientific quest, seeing only what their unaided vision could perceive, and yet feeling drawn to study it, to give it meaning. In Greek and later Western tradition, Sagittarius was woven into mythological narratives with particular tenderness. The archer was sometimes identified as Crotus, a wise creature associated with music and learning, placed in the heavens as a reward for his contributions to culture. In other versions, Sagittarius represents the centaur Chiron, half-wise teacher, half-wild creature of nature, forever aiming his arrow into the depths. The iconography carries within it a strange duality, the civilized and the untamed, the conscious aim toward knowledge and the instinctive wildness beneath reason. When we gaze at this constellation now, knowing what we know, there is something almost prophetic in that ancient imagery, a force of civilization and reason, represented as a figure drawing a weapon of precision and intention, pointing directly at the location of the most gravitationally bound object nearest to us, pointing inward. Islamic astronomers inherited these traditions and added their own observations. They watched Sagittarius with particular attention because this region of the sky contains not only bright, distinctive stars, but also a concentration of fainter stars and dust clouds that would have been visible to dark-adapted eyes from desert skies. The region feels textured, dimensioned, alive in a way that other parts of the celestial vault do not. It would be centuries before spectroscopy and radio astronomy would explain why this is so. The dust lanes and stellar concentration are genuine markers of the galactic structure itself, a genuine window into the thickening of material as one moves deeper toward the galactic core. But the ancients felt this truth rather than understood it. Their eyes reported accurately what their science could not yet name. What emerges from studying these ancient observations is a quiet realization. Humans have always possessed an intuitive sense for significance. We felt that Sagittarius held something important, something central, long before we had the instruments to prove it. The stars in this region did seem to congregate more densely than elsewhere. The star Antares, brilliant and ruddy, anchors the constellation with a crimson glow that stands out against the background of distant suns. And yet, if you look carefully, the region toward the brightest concentration of stars in Sagittarius, the direction of greatest stellar density, appears almost to obscure itself with dust and darkness, as though guarding something, as though hiding something precious behind a veil of cosmic material. Perhaps what drew our ancestors to watch this place so carefully was something even more subtle than visual observation. The human mind seems to possess an attunement to deep structure, a sense for when something fundamental underlies what we can see directly. We felt the weight of it. We felt the center, and in response, across multiple cultures and centuries, we created mythologies that spoke of archers and aims, of direction, of purpose pointing inward. None of these ancient stargazers could have articulated why this direction felt so significant. They simply knew it. They watched the stars in this region through the seasons, traced the pattern of the archer across the night sky, and left behind records and stories that would echo down through history. And when, finally, telescopes and radio dishes became sensitive enough to listen to what actually dwells at the heart of Sagittarius, what we discovered was something that justified, in the most profound way, the intuitive sense that something extraordinary gathered there. Patience had its reward. The ancient watchers were right. And so began the patient work of watching. Night after night, decade after decade, astronomers pointed their telescopes toward that invisible center and waited for starlight to tell them its secrets. The task was deceptively simple to describe and enormously difficult to execute. Locate individual stars near the galactic core, measure their positions with exquisite precision, and track how those positions changed over time. From that patient accumulation of numbers, tiny shifts in light, mere pixels on a photographic plate, would emerge the proof that something extraordinary dwelt at the heart of our galaxy. The work required a particular kind of temperament. These were not astronomers seeking sudden revelation or dramatic discovery. They were methodical observers, comfortable with the slow unfolding of data, willing to spend years on measurements that might not yield answers until decades had passed. Each night, they would return to the same region of sky, photograph it again, compare it to previous images, look for the faint trails of motion that only become visible when you can see an object's position across 20, 30, sometimes 40 years of observation. Consider the sheer patience this demanded. A star's motion across the sky, when viewed from Earth, might be almost imperceptibly small. We are talking about angular shifts so tiny that they rival the width of a human hair held at arm's length. And yet these measurements had to be accurate enough to calculate orbital mechanics, to derive mass from motion, to draw conclusions about the invisible object those stars were dancing around. The telescopes had to be stable, the measurements had to be consistent, the observers had to resist the temptation to see what they wanted to see, rather than what the data actually showed. The technology evolved slowly but steadily. In the earliest days, astronomers used photographic plates, painstaking glass negatives that captured starlight and could be compared by eye, by measurement, by the human brain's ability to spot differences between two images laid side by side. As decades passed, electronic detectors replaced glass plates. Computers helped with the mathematics, but the fundamental method remained unchanged. Look, measure, record, wait, look again. The passage of time itself became the tool. There is something almost meditative in contemplating this work, is there not? The rhythm of it. The acceptance that understanding would come, not in a moment of breakthrough, but through the gentle accumulation of patient observation. Night after night, the same patch of sky, the same commitment, the same quiet faith that if you watch long enough, the universe will reveal what you are looking for. By the 1990s, astronomers had identified dozens of stars orbiting invisibly near the galactic center, their paths emerging from years of positional data, like long brushstrokes appearing on a canvas. Each star had its own orbit, its own period, its own peculiar motion. Some orbited swiftly, their paths tight and fast. Others moved more slowly through their longer, more distant journeys. Together, they formed a portrait of gravity itself, visible proof that some enormous mass, invisible but undeniable, sat at the center, pulling on everything around it. The infrared wavelengths became crucial to this work. The galactic center is obscured by dust, vast clouds of cosmic material that block visible light as effectively as clouds block the view from an airplane. But infrared radiation passes through that dust almost unimpeded, and by observing in these longer wavelengths, astronomers could finally see clearly what had been hidden for all of human history. The stars that had always been there, orbiting their invisible master, suddenly became visible to our instruments, if not to our eyes. What must it have felt like for those astronomers, peering at years and years of accumulated data, watching a star's position drift slowly across one image after another, to realize that you were witnessing something real, not a theory, not an inference, but actual objects moving through actual space under the influence of actual gravity. The black hole had not moved. It remained where it always was, utterly still, utterly patient. But its influence was written in the trajectories of stars, in the slow dance of light orbiting around darkness. The measurements accumulated through the 1990s and into the new millennium. Tens of stars now documented, hundreds of nights of observation, thousands of individual position measurements, each one a small piece of a larger puzzle. The data did not whisper its conclusions. It built them slowly, steadily, until doubt became impossible, and certainty emerged not as a flash, but as an inescapable accumulation of evidence. Something remarkable was hiding at the galactic center, and the stars were beginning to reveal its identity to those patient enough to listen. Among all the stars wheeling around that invisible giant at the heart of our galaxy, one in particular has become the astronomer's most patient teacher. Its name is S2, a designation that might seem cold and bureaucratic until you understand that this single point of light has spent more than 2 decades revealing the deepest secrets of Sagittarius A. And the story of S2 is, in many ways, a story about patience itself, about what humans can learn when they simply watch, night after night, year after year, allowing the universe to show its workings at its own unhurried pace. S2 is what we call a blue supergiant, a star far more massive than our own sun, burning with an intensity and brightness that would dwarf Earth's star into near invisibility if placed beside it. Yet for all its brilliance, S2 lives in deep shadow. It orbits so close to Sagittarius A that the gravitational pull is almost incomprehensibly strong, a pull so constant and so perfectly balanced that S2 traces an elegant elliptical path around that dark center, the way a planet orbits around a sun, except that what S2 orbits is no ordinary sun at all. It is something far stranger and far more compact. The orbit of S2 takes approximately 16 years to complete, 16 years for that star to sweep out its entire path and return, in a sense, to where it began. Now consider the patience required to measure this. Astronomers cannot simply observe S2 for a few nights or a few months. They must return, night after night when conditions allow, year after year, decade after decade, tracking the position of a star so distant and so faint that it appears as nothing more than a tiny fluctuation of light in their telescopes. And yet from these measurements, from countless observations accumulated across years, emerges something almost miraculous. The mathematics of orbital motion is elegant. When you know how fast an object orbits and how large its orbit is, you can calculate the mass of the thing it orbits around. This is not speculation or guesswork. This is the language of gravity itself, written into the motion of objects through space. In the 1990s, as telescopes improved and tracking methods became more precise, a team of astronomers, many working at the European Southern Observatory in Chile, began to gather data on S2's position with increasing accuracy. They used a technique called infrared adaptive optics, which uses laser beams to correct for the distortion caused by Earth's atmosphere, allowing the telescope to see with much greater clarity. The data accumulated slowly, methodically, almost hypnotically in its regularity. And as the years passed and S2 continued its stately orbit, as decade markers passed and the star returned closer and closer to its closest approach to Sagittarius A, the calculations grew more and more precise. You could almost watch the mystery unraveling, not with any drama or sudden revelation, but with the gentle inexorability of a mathematical proof being written out, step by step. The closer S2 came to its perihelion, its closest point to Sagittarius A, the more its motion would be affected by the black hole's immense gravity, and thus the more accurately that gravity could be measured. By the early 2000s, the pattern was becoming unmistakable. S2's orbit could only be explained if an enormous mass was sitting at the center of the galaxy, a mass so great that it had to be concentrated into an impossibly small space. The numbers began to clarify. The gravitational master that held S2 in its elegant dance had to be millions of times more massive than our Sun. The measurements grew tighter, the error bars shrank, and gradually, with the same quiet inevitability of a sleeper drifting deeper into rest, the mass of Sagittarius A emerged from the data like a photograph developing in solution. What is remarkable about this process is that it required no equipment beyond what was essentially available decades earlier. It required no sudden breakthrough, no eureka moment of discovery. What it required was something perhaps even rarer: sustained, patient observation. The willingness of human astronomers to return to the same question, night after night, year after year, accumulating data in tiny increments, each observation no more dramatic than the last, yet collectively, over time, painting an unmistakable picture of the reality hidden at the heart of the Milky Way. There is a meditative quality to this kind of work. Imagine the rhythm of it. The same instruments calibrated and directed, the same coordinates in the sky visited again and again. The slow accumulation of numbers, of measurements, of tiny refinements to the understanding. This is how nature reveals itself to those patient enough to listen, not through grand gestures, but through the quiet accumulation of evidence. through the language of mathematics, written in the motion of light across space. S2, in its long elliptical journey, was like a weight on the end of a string, and by measuring its motion through space, astronomers had discovered they could weigh the very center of our galactic home. And so, night after night, as decade folded into decade, the astronomers gathered their numbers. Each position of S2, each careful measurement of its gentle swing around that invisible anchor, was a thread in a vast and patient tapestry. The mathematics, when you step back from its complexity, is remarkably elegant in its restraint. If you know how fast something orbits, and how long it takes to complete one full circle, the mass of what it orbits around becomes almost inevitable. The equations whisper it to you. They're not shouting, they're simply translating motion into gravity, and gravity into mass. The numbers that emerged were staggering, yet somehow deeply quiet in their presentation. 4.3 million times the mass of our Sun. 4.3 million. Picture that for a moment. Not billions, as some of the supermassive black holes dwelling in distant galaxies contain. Not trillions. 4.3 million suns, each one a vast sphere of nuclear fusion, billions of miles in diameter, compressed, crushed, folded into a region smaller than the orbit of Mercury around our own star, smaller than the distances the innermost planets of our solar system traverse. That incomprehensible density, that merger of scale and compression, arrived not from dramatic observation, but from patient celestial bookkeeping. What's remarkable is how astronomers speak of this result. There's no breathlessness in their papers, no alarm. It's as though the universe has already absorbed this knowledge and moved on, and so the scientists follow. They present the mass in cool, measured language. A few million solar masses, they say, almost casually, as if discussing the weight of a small city rather than the gravitational anchor of a galaxy containing 200 billion stars. The calmness is not indifference, it is the calmness of understanding. When you have tracked something methodically for years, mapped its path with millimeter precision, felt the mathematics align with observation again and again, a kind of peace settles over the findings. The compression itself is a thing that astronomers have learned to sit with comfortably, though it challenges the ordinary sense. Our Sun, that familiar furnace of light and heat that has warmed every day of human existence, could fit inside the Earth 1.3 million times over. Now imagine taking 4.3 million of those suns and folding them into a sphere no larger than your own planetary neighborhood. The density is almost abstract, almost philosophical. It exists beyond the realm of human intuition, which means the mind, in confronting it, must release its need to feel the size and simply accept the mathematical truth. And in that release, there is a strange kind of rest. The measurements themselves became more refined as the years accumulated. By the time the 21st century had settled in, astronomers had refined the mass estimate to astonishing precision. Not 4.3 million, give or take a few 100,000. 4.3 million plus or minus about 80,000 solar masses. The uncertainty bars grew tighter and tighter. The star S2 continued its stately dance, and with each return to aphelion, each journey to the closest point in its approach, the evidence deepened. The gravity was real, consistent, fundamental. It did not waver or surprise. It simply was, as gravity always is, the most patient and most inevitable of forces. What the astronomers had accomplished, without fanfare, was to weigh the invisible. They had measured the immeasurable. They had taken an object so extreme, so hostile to our instruments and our presence, and they had calculated its mass with the same precision a chemist might weigh a substance on a sensitive scale. The methods were sound, the logic was unassailable, and the result sat at the heart of the galaxy like a secret that was always there, waiting quietly to be discovered through the simple act of watching one star move in a circle, again and again and again. Now, 4,300,000 suns pressed into a space smaller than our own solar system. This number might seem at first to carry a kind of weight, a gravitational heaviness that makes one pause. And yet, here lies one of the more soothing truths about Sagittarius A. When we place it alongside its cousins scattered throughout the observable universe, it becomes something gentler than we might have imagined, something almost modest, even serene in its proportion. Consider for a moment the black hole at the heart of the galaxy Messier 87, a vast elliptical system some 55 million light-years from Earth. There, at that distant galactic core, sits a supermassive black hole of such magnitude that it contains the mass of 6.5 billion suns, all crushed together. 6.5 billion. When we contemplate that figure, Sagittarius A begins to seem almost delicate by comparison, almost gentle in its quietude. The supermassive black hole lurking within the galaxy NGC 4889, even farther away, may hold within itself more than 21 billion solar masses. 21 billion. The mind stretches toward incomprehension, and yet this is the universe's way of showing us something quietly reassuring. Sagittarius A, the great unknown that sits at the center of our own Milky Way, occupies a place of relative restraint in the cosmic hierarchy. It is powerful, yes, immeasurably so, but it is not the most powerful. It is not the most extreme. And perhaps there is a certain calm to be found in that realization. Here we live, you and I, in a galaxy with a relatively moderate supermassive black hole at its core. We are not orbiting around a gravitational monster of 20 billion solar masses. We exist in a kind of middle ground, a balanced place where the forces at play, while enormous, are somehow more comprehensible than their extremes elsewhere might be. There exists, too, a fascinating phenomenon that distinguishes Sagittarius A from many of these other galactic cores, where some supermassive black holes feed voraciously, consuming matter and blazing with radiation. Our own black hole has become something of an understated presence. It draws in far less material than one might expect given its mass and location, and so it remains, in a sense, sleepy, contented, not constantly gorging itself, but settled into a quiet rhythm of slow accretion. Think of the difference between a black hole in an active galactic nucleus, one that is surrounded by swirling disks of superheated matter, blazing with X-rays and visible light, flaring unpredictably across the electromagnetic spectrum. These are the dramatic ones, the ones that demand attention through their sheer ferocity. Sagittarius A, by contrast, is almost placid. It sits at the galactic center with a kind of patience, a stillness that has allowed billions of years of relatively stable galactic life to unfold around it. And this, too, is part of what makes the study of Sagittarius A so deeply calming. We are not living in a galaxy with a raging monster at the helm. We are living with a steady, measured force, a gravitational anchor that holds our spiral arms in their graceful dance, but does not thrash or violently demand our attention. It is almost as if the universe has provided us with the ideal supermassive black hole for a kind of contemplative existence. Not too large, not too active, balanced, proportional. Some of the most distant supermassive black holes ever discovered, those lurking in the hearts of the earliest galaxies in the universe, appear in certain cases to exceed even these figures we have discussed, holding billions upon billions of solar masses in the very ancient cosmos. Yet we do not live there. We live here, in this present epoch, with Sagittarius A as our black hole, and that is, when we truly consider it, a quiet gift. the fear that sometimes accompanies the knowledge of a black hole at the galactic center, and it is understandable this fear, begins to dissolve when we place it in its proper context. We are not unique in harboring such an object. We are not cursed by it. Rather, we are among the countless galaxies that have learned to coexist with these invisible anchors, these gravitational centers of being. And many of us, many of these galaxies, are doing rather well. And so the question became, how do you look at something that small, that distant, that collapsed into silence? The answer arrived not as a single telescope, but as a conversation between 8 radio dishes scattered across the Earth, each one listening to the same whisper of radio waves emerging from the galactic center, waiting patiently through the night. In 2017, astronomers and engineers began orchestrating what would become the Event Horizon Telescope. It was less an invention than a realization that you could link together observatories on different continents, synchronizing their clocks to nanosecond precision, and listen to the same cosmic radio source simultaneously. Imagine, for a moment, how lonely a single radio dish can be, collecting faint signals from the void. Now imagine giving that dish a partner across an ocean, and another on a different continent, and another. Soon you have 8 dishes spread from the South Pole to Chile to Hawaii to Spain, all turning their faces toward Sagittarius A in perfect, patient unison. The beauty of this approach, and there is profound beauty in it, was that you didn't need to build a single massive telescope the size of Earth. Instead, you could borrow Earth itself. By separating these dishes by thousands of kilometers and binding their observations together mathematically, scientists could achieve a resolution as if they had constructed one enormous instrument with a diameter spanning the planet. 8 telescopes became one eye, distributed across continents and oceans, yet somehow unified in purpose. How did they synchronize so precisely? Atomic clocks. Each observatory carried atomic clocks that never drift, that measure time in billionths of a second. The radio waves arriving at each dish were recorded with timestamps so exact that when the data was later combined in supercomputers, the tiny delays between arrivals could be measured, analyzed, and used to triangulate exactly where the signal had originated. It was like hearing an echo arrive at 8 different ears and using the microseconds of difference between arrivals to pinpoint the source in perfect 3-dimensional space. The collaboration itself was a kind of orchestration. Scientists from dozens of countries, dozens of institutions, all agreeing to point their instruments at the same invisible target and sit in patient observation. There was no drama in the moment, just steady, quiet work. Night after night, the dishes collected the faint radio whispers from Sagittarius A, storing terabytes of data on hard drives. The actual analysis would come later, in the silence of computation. But the observation itself was a kind of meditation, 8 witnesses, watching together. What made this moment so different from all previous attempts was the addition of new radio observatories to the network. Facilities in the northern hemisphere joined with those in the south. Sensitive new receivers were installed. The array became more sensitive, more detailed in its listening. And crucially, for the first time, the frequency was increased high enough that the wavelengths being observed could theoretically resolve the structure around the black hole's event horizon itself. They weren't just listening for radio waves anymore. They were listening for the shape of space itself. The data from those 2017 observations would take years to process. Hard drives filled with recordings had to be shipped around the world, synchronized and analyzed through supercomputers in coordinated facilities. It was slow work, methodical, utterly without urgency. Months turned to years, and still the team waited, refined their methods, checked their calculations, and trusted the mathematics. But in those months of observation, Something remarkable had already happened. The human species had created a tool that could touch something untouchable. Not physically, no rocket could ever approach Sagittarius A in any human timescale, but intellectually, through patience and coordination and the patient accumulation of photons across light years of distance, we had reached out and made contact. We had built a way to see. When astronomers set out to see the unseeable, they didn't build a bigger telescope. They built a network. They took radio dishes scattered across the continents in Chile, Hawaii, Arizona, Europe, the South Pole, and through a technique as elegant as it is patient, they wove them all together into a single instrument of extraordinary power. This method has a name that carries within it the whole philosophy of the work: very long baseline interferometry. And at its heart lies something almost poetic in its simplicity. You take waves of radio light arriving at different places on Earth, at subtly different times, and you ask them to speak to one another. Imagine you're standing in a vast room, and someone across the ocean is playing a single, distant note. The sound reaches you, but it reaches your left ear a fraction of a second before your right. Your brain takes this tiny difference, this whisper of delay, and it tells you where the note comes from. Your two ears, separated by mere inches, are an interferometer. They resolve direction from difference. Radio astronomers do the same thing, but their ears are separated not by inches, but by the width of continents. They are thousands of kilometers apart, and the waves they're listening to are so faint, so ancient, that they must capture them with obsessive precision. Here's where the patience becomes apparent. A radio dish in Chile receives a signal from Sagittarius A. At almost the exact same moment, within billionths of a second, a radio dish in Hawaii receives the same signal. The challenge is that both signals are impossibly weak. Both are just whispers of energy that have traveled 26,000 years to reach Earth. To truly hear them, to find the pattern hidden in the noise, astronomers must record not just the signal itself, but its precise moment of arrival, tagged with atomic clock accuracy. Every observation must carry with it the fingerprint of time. This is what makes the whole enterprise possible. The recordings from each individual telescope are stored on hard drives or tape, and during the Event Horizon Telescope project, they were sometimes shipped physically because the volume of data was too vast to send through any network. Picture that for a moment. Scientists waiting for hard drives in the mail, containing observations that would answer one of astronomy's oldest questions. Once all the data arrived at a central location, the real conversation began. Computers worked through the recordings, comparing the signals from different telescopes, looking for the moments when the radio waves from the same distant source had registered in different locations at different times. And in those tiny, precious differences lay the structure of the invisible. This process is called correlation. It's less like vision and more like listening to an orchestra, where each instrument is in a different building, separated by mountains and oceans. When you correlate the signals, you're not just combining them, you're allowing them to interfere with one another. When a peak from one telescope arrives at precisely the right moment to meet a peak from another, they reinforce each other, and the signal brightens. When a peak meets a valley, they cancel, and the signal fades. By mapping all these patterns of reinforcement and cancellation, you can construct an image. You can infer the shape and structure of something so far away and so small that no single telescope, no matter how large, could ever resolve it directly. What's remarkable is that this technique works not because Earth is large, though it is, but because of the wavelengths being observed. Radio waves are much longer than visible light. They're measured in millimeters or centimeters rather than the nanometers of light we see with our eyes. This means you can observe a distant object at radio wavelengths and still resolve fine detail, as long as your observatories are spread far enough apart. It's one of nature's quiet compensations. The very thing that makes radio waves invisible to human eyes, their longer wavelength, is what allows them to be used to probe the universe's deepest mysteries. If astronomers had tried to look at Sagittarius A, invisible light, they would have been defeated. The dust clouds would have blocked the view, but radio waves pass through dust as though it weren't there. They arrive from the galactic center, carrying information that light cannot bring. And so the Earth becomes something it has never been before. It becomes a single, unified eye, not by moving its telescopes or building a new machine, simply by coordinating what it already has. Radio dishes in the Atacama Desert and on Mauna Kea, in the mountains of Spain and at the geographic South Pole, in Africa, in Australia. Each one captures a tiny piece of the signal. Each one is a pupil, and together they form an aperture so vast that it can resolve angular distances on the sky of just microarcseconds. To understand how small that is, it's like being able to see a golf ball on the moon, or to distinguish the two headlights of a car, not just at any distance, but specifically at the distance of billions of miles away. This is where very long baseline interferometry reveals its true gift. It is not a workaround for the limits of engineering. It is a meditation on how to listen better. It teaches that to see the universe's most intimate secrets, sometimes you don't need to go farther out into space. Sometimes you need to wait. You need to synchronize. You need to listen to what is already arriving. You need to let the signals from different parts of the world converse with one another and find meaning in their conversation. In that convergence lies not just data, but a kind of cosmic poetry. The universe has been broadcasting its secrets all along. It took the whole planet, standing still and listening together, to finally hear what had been calling across the darkness for so long. And then, after more than a century of wondering, after decades of patient starlight measurement and mathematics, written in the margins of notebooks and displayed on screens in darkened control rooms across the world, the image arrived. It came not as a surprise, but as a kind of confirmation, whispered by the cosmos itself. In May of 2022, in simultaneous press conferences across the globe, from Washington to Tokyo to Santiago, the first photograph of Sagittarius A was unveiled to the watching world, and what emerged on the screens and in the projections was something far simpler, far more beautiful than almost anyone had expected. It was a ring, a soft, glowing ring suspended in darkness. The light itself, and here is where the poetry deepens, was not the light of the black hole itself, which by definition produces no light at all, but the light of gas and matter caught in the gravitational field around it, bending and accelerating as it spiraled inward. The photons, those messenger particles of light, were being bent by gravity itself, their paths curved by the immense weight of space-time compressed at the center. What you were seeing in that image was not the shadow of the black hole, though that is what it is often called, but rather the silhouette of light that had been captured and redirected by the gravity surrounding the event horizon. The ring glowed with an uneven brightness. One side appeared slightly brighter than the other, a detail that matters profoundly when you understand what it means. The brighter edge is the side where material rotates toward us, moving at nearly the speed of light, and the light itself is compressed and brightened by that relativistic motion, a phenomenon called beaming or relativistic Doppler effect. The dimmer side recedes away from us, and its light is stretched and weakened. So even in this single snapshot, you are witnessing the actual rotation of material around a black hole, motion caught in a photograph, a frozen instant of something eternally in motion. The darkness at the center, the true shadow, was smaller than some astronomers had predicted, a fact that carried meaning. The size and shape of that dark region told those who knew how to read it something about the black hole's spin, about how rapidly Sagittarius A rotates on its axis, and the image itself was not captured by a single telescope, but was constructed from data gathered simultaneously by radio dishes arrayed across the Earth, all of them pointing at the same speck of sky in the Sagittarius constellation, all of them listening together, and then that data was painstakingly reconstructed using algorithms and mathematical techniques that allow billions of tiny measurements to be stitched into a single coherent picture. What the image truly represents, when you step back from the technical details, is something gentler and more profound than conquest or revelation. It is confirmation that the universe operates according to principles we can understand. Einstein, nearly a century before this photograph was taken, wrote down equations that described how gravity bends light, and those equations, tested and refined and verified countless times, predicted exactly what we would see if we ever looked directly at the event horizon of a supermassive black hole. And when we finally looked, the universe answered back, yes, this is how it works. The equations were right. The mathematics held true even in the most extreme environment we know. The announcement of the image was not accompanied by alarm or spectacle. It was presented as what it was, a fulfillment of a prediction, a moment when theoretical physics and observation converged, when something that had existed for millions of years but had never been directly seen was finally rendered visible. Scientists spoke of it with a kind of quiet satisfaction. There was wonder in their voices, certainly, but also a sense of things falling into place, of a long investigation reaching a natural conclusion. And what you see in that image, if you study it for a moment, is not something chaotic or violent, despite the immense forces at play. The ring is smooth. The darkness at the center is calm and still. There is no flashing, no explosion, no sense of immediate danger. It is a kind of visual representation of equilibrium, of material falling and spiraling and radiating energy, but in a way that has established itself over millions of years into a stable pattern. The glowing ring is not a moment of crisis. It is a kind of steady state, a dance that has been choreographed by gravity and has continued night after night for eons. Now, if you were to fall toward that boundary, that precise threshold where light itself begins to falter, what would you actually experience? This is perhaps one of the most peaceful truths about black holes, and it often surprises people who imagine them as cosmic maelstroms of chaos and violence. The event horizon, that famous point of no return, is in fact quite serene. It is simply a surface, a mathematical surface, a place where gravity has grown so profound that the speed required to escape exceeds the speed of light, and so nothing that crosses it can ever return. But here is the remarkable quietness. If you were watching from a safe distance, from Earth or from the orbit of a distant star, nothing visibly dramatic would occur at that moment of crossing. There would be no flash, no explosion, no sudden catastrophe visible from afar. The person falling would experience, in fact, remarkably little at that precise threshold, a gradual compression, yes, owing to the differences in gravity between their head and their feet, but not an instant of terrible rupture. Time itself would appear to slow infinitely from the perspective of someone watching, but the infalling observer would perceive themselves crossing with what physicists call a finite proper time. It is a gentle transition between two states of being. What makes this even more intriguing is the phenomenon of photon rings. Light, despite its incomparable speed, can orbit a black hole at a particular distance, trapped in an unstable equilibrium. These photons trace a path so close to the event horizon that they circle endlessly, and some of the light we captured in that 2022 image, that luminous ring, comes from photons that have been orbiting Sagittarius A multiple times before escaping toward us or spiraling inward. They create, in a sense, a theatre of light suspended in time, a corona of grace around the threshold. The brilliant ring you saw in the photograph is not actually the event horizon itself, but rather the glowing emissions of matter just outside it, and the shadow at the center, that darkness within the light, that is what we call the photon ring's projection, the silhouette of space-time bent so severely that no light can emerge. To stand at the edge and look inward would be to see an infinite amplification of the universe behind you, stretched and compressed into a dizzying corona, while darkness pooled before you like obsidian water. But here is the particular comfort of this physics. Because Sagittarius A is so far away, none of this interior drama affects us. The event horizon lies 26,000 light-years distant. No tidal forces reach us. No light is stolen from our skies. The boundary exists in perfect isolation, a mathematical perfection woven into the fabric of space-time, indifferent to observers, asking nothing of the galaxy that orbits around it. The event horizon is not a place of violation or chaos, but rather a place of absolute order, a frontier where the rules of existence undergo a transformation so complete that we might think of it less as destruction and more as profound translation. And perhaps that is the deepest peace this image offers, that at the heart of our galaxy, where gravity has rewritten the laws of physics into their most extreme form, there is no fury, only the elegant and inevitable consequence of mass and space-time and the nature of light itself. And here emerges something rather remarkable, something that might seem almost counterintuitive when you first consider it. This colossal gravitational engine at the heart of our galaxy is almost quiet, restful even. It feeds far less voraciously than one might expect of something so enormous, and this quietude, this restraint, tells us something profound about how the universe actually arranges itself in the real and ordinary world, as opposed to how we sometimes imagine it must work in theory. When astronomers first began to study supermassive black holes across the distant universe, they discovered that many of them are remarkably active consumers. Feeding and feeding almost continuously, these black holes pull in vast clouds of gas and dust and stellar debris, creating what we call active galactic nuclei. The infalling material heats to extraordinary temperatures, and the friction and magnetic turbulence generate powerful jets of radiation that can shine for billions of light-years, outshining entire galaxies. We call these quasars, and they are among the brightest objects in the cosmos. They are violent, dynamic, and restless. One might assume that Sagittarius A, being so massive, would be among the hungriest and most violent of all. Yet observations have revealed something quieter altogether. Sagittarius A consumes material at a rate that is, by the standards of supermassive black holes, almost abstemious. It feeds, yes, but slowly, gently. The radio astronomers studying it measure its activity as relatively low. The accretion rate is perhaps just a few times the mass of Earth per year, which sounds enormous, until you consider that some other supermassive black holes consume millions of solar masses annually. In cosmic terms, Sagittarius A is something of a sparse eater. Why might this be? Several ideas suggest themselves to patient observation. One lies in the nature of the galactic core itself. The region immediately around Sagittarius A is not overflowing with dense clouds of gas waiting to tumble inward. The black hole has, over millions of years, consumed or scattered much of the loose material that once orbited it. What remains is more orderly, more dispersed. The stars and gas clouds move in their long, elegant orbits, but they do not crowd it inward in a chaotic rush. The black hole's immediate environment is, in a word, relatively starved, and this starvation is itself a kind of stability. Consider the contrast. In the hearts of many distant galaxies, Particularly in the early universe, supermassive black holes found themselves surrounded by abundant reservoirs of gas. A young galaxy in the universe's youth was often a roiling, turbulent place, with frequent galaxy collisions stirring things up, sending vast quantities of material spiraling toward the core. Under such conditions, a black hole could feed prodigiously, and the energy it released would shape the galaxy's entire future. But in our own Milky Way, in our own quiet corner of the cosmos, that turbulent era has passed. We are in a mature galaxy now, one that has settled into relative tranquility. There is something deeply soothing about this recognition. The supermassive black hole at the center of your galaxy is not a raging, apocalyptic engine threatening to devour the entire system. It is, instead, something almost dormant by the standards of its kind. A monster, yes, but a sleeping, or mostly sated one. It will continue to pull in material over timescales of millions and billions of years, but not in any hurried or dramatic fashion. The process is gradual enough that it might almost be called patient. This quiet state also means that the violent radiation and jets that characterize active black holes are largely absent from Sagittarius A. The black hole is not generating the intense X-rays and gamma rays that would flood the galaxy with high-energy particles and turbulent magnetic fields. The galactic center remains, despite its extraordinary gravity, a relatively benign place from the perspective of the rest of the Milky Way. Life on Earth has never been disrupted by catastrophic radiation from the black hole at the galaxy's core, nor is it likely to be for the foreseeable future. This restfulness might also reflect something about the nature of black hole accretion itself. Matter does not automatically spiral into a black hole the moment it ventures near. Instead, it tends to form what we call an accretion disk, a slowly rotating region where friction gradually removes orbital energy and material spirals inward. But if that disk is sparse and slowly fed, the process becomes almost meditative. It takes time, there is no urgency, the black hole waits, and material arrives when it arrives, and the system maintains a kind of equilibrium. And perhaps there is an even deeper implication in this quietude. Consider that the universe is not filled with raging, explosive events at every scale and location. Instead, most of the time, exists in states of relative calm. Even the most extreme objects, black holes, neutron stars, the cores of galaxies, often spend their existence in quiet, steady states. The universe is not primarily a place of violence and disaster, despite how vividly we sometimes imagine it. It is, more fundamentally, a place where gravity and thermodynamics have reached equilibrium, where systems settle into sustainable patterns, where quiet persistence is the norm and dramatic change the exception. Yet even in its quietness, Sagittarius A is not entirely still. There is a gentle flickering that astronomers have come to know as flares, sudden bursts of light and energy that rise from the region near the event horizon and then fade again, like embers briefly brightening in a dimming fire before settling back to ash. These flares occur irregularly, sometimes hours apart, sometimes stretching across days with nothing visible at all. What causes them remains a mystery, wrapped in the mathematics of gravity and magnetism, and perhaps that uncertainty itself is restful, a reminder that the universe still holds secrets that no urgent need to solve will make clearer. The flares themselves are not dangerous. They are not directed toward us. They are simply part of the slow-breathing rhythm of a region so distant that their light takes 26,000 years to reach your eye, which means you are watching something that happened while humans were still in the Stone Age, still gathering around fires not so different from these ancient cosmic flares. Around Sagittarius A, there are also clouds of gas and dust in orbit, great diffuse structures that swirl and drift in the immense gravitational field, like thought itself might drift through the mind in sleep. These clouds move with a slowness that seems almost patient to human timescales, yet they are hurtling around at thousands of kilometers per second. One particularly well-studied cloud, known as G2, approaches the black hole on an orbit that takes decades to complete, and astronomers watched with quiet fascination as it drew closer in the years around 2014, close enough that they wondered whether it might be torn apart by tidal forces. Yet it survived. The cloud bent and stretched and sang, metaphorically, through gravitational waves and X-rays, but it did not fall in. It swung around and began its long journey outward again, teaching us that resilience exists even in the throat of one of the universe's most extreme objects. And as you drift with this knowledge, consider what the far future holds for Sagittarius A and the Milky Way itself. The black hole does not feed hungrily. It does not rage against the universe. It simply sits at the center of our galaxy, slowly, almost imperceptibly, accumulating the occasional star that wanders too close, the occasional cloud of gas that spirals inward. At its current rate, it would take many billions of years, far longer than the remaining lifespan of the Sun, for Sagittarius A to consume any significant portion of our galaxy. The future of the Milky Way is one of gradual change, not cataclysm. Billions of years hence, our galaxy may collide with Andromeda, that great neighboring spiral, and the two will merge into a single larger galaxy, while the black holes at their centers also eventually merge, a slow cosmic waltz unfolding across millions of years. But that is so distant in time that it belongs more to poetry than to worry. What settles the mind about Sagittarius A is precisely this timescale, this profound slowness. The universe operates on rhythms so much longer than human breath, human heartbeat, human worry, that to contemplate it is to feel time itself expanding around you. The black hole at the galactic center has been there for most of the age of the galaxy itself, and it will be there long after you, long after your children's children have become dust themselves. It orbits no star. It falls toward no greater darkness. It simply exists, patient and ancient, warping the space-time around it, with a constancy that suggests a kind of contentment with its own nature. Even its flares, those bright interruptions in the darkness, come and go without urgency, rising and fading like the slow arc of consciousness itself, drifting between waking and sleep. The astronomers who study it night after night, year after year, learn to move with this unhurried pace. They gather their data, they make their measurements, they publish their findings, knowing that the answers to the deepest questions about Sagittarius A may take decades or centuries to fully emerge. There is no emergency. There is only the gentle accumulation of understanding, the quiet satisfaction of knowing a little more about how the universe holds itself together. And in that patient accumulation, in that refusal to rush toward answers that nature herself is in no hurry to reveal, there is a kind of peace that settles into the bones, a reminder that some of the most profound truths require us to simply sit still, to listen, and to let the vast architecture of reality reveal itself in its own time. And so we might imagine ourselves withdrawing now, very slowly, from that patient heart of light and shadow at the galaxy's core. The image of Sagittarius A, that soft ring of illuminated gas, begins to fade as we turn our gaze outward through space and time, the way one might gradually close the door of a room and walk down a long corridor toward home. Around the galactic center, the stars continue their ancient orbits, S2 completing its careful ellipse every 16 years, the smaller stars threading their paths through the darkness, and all of it continues without hurry, without urgency, exactly as it has continued for billions of years before we ever learned to listen. We drift past the dense cluster of stars that surrounds that supermassive well of gravity, and the light from Sagittarius A becomes a distant glow behind us now, no longer the center of our attention, but rather one more steady presence among countless others. The spiral arms of the Milky Way reveal themselves as we pull back further, those graceful curved lanes of stars and dust, rotating with a patient slowness that takes 250 million years to complete a single turn. From here, our solar system appears as merely one small point among billions, our sun unremarkable, our Earth smaller still, and there is something deeply restful in that perspective, is there not? The knowledge that we occupy a corner of vastness so immense that the most powerful forces in our universe are measured not in explosions or chaos, but in the slow pulling of gravity, the steady waltz of orbital mechanics, the patient accumulation of time. Behind us, Sagittarius A continues to exist exactly as it did before anyone ever named it or measured it. It fed perhaps a little less actively this week than last. Or maybe the clouds of gas circling its edge brightened with a gentle flare that would go unnoticed by our instruments for months. These things occur without observation, without witness, in the same way that the universe moved before consciousness arose to study it. There is a peculiar comfort in that thought as you drift further from the galactic center, the understanding that the cosmos does not require our attention to be profound, to be real, to be beautiful in its own way. The light years accumulate now in your retreat, thousands of them, then tens of thousands. We pass back through the spiral arms, drift past the molecular clouds where new stars are gently being born from dust and gravity and time, and the center of the galaxy becomes simply a feature of the larger structure, no longer commanding the whole of our vision. Around us, countless other galaxies appear as we pull back further still, elliptical ones and spirals of their own, each with their own hidden hearts, their own supermassive centers of gravity, their own stories of light bending in the presence of extraordinary density. How curious it is that the most violent places in the universe, these regions where gravity has won a complete victory, where matter has surrendered all resistance, often turn out to be the quietest. Presents to us no fireworks from where we orbit, no violent jets of radiation destroying the neighborhood. It sits instead like a patient center of balance, holding the galaxy together with the sheer weight of its presence, asking nothing, offering only the steady constancy of its gravity. The astronomers who spent decades tracking those star orbits in infrared light, who built instruments across the globe to listen to its whispers, who finally beheld that ring of light bent around darkness. They were not chasing danger or drama. They were simply trying to understand how the universe is made, with the same curiosity a person might have when watching the movement of clouds across an evening sky. And now, as we continue our slow journey backward through space, we might imagine the Earth growing larger in our vision, returning to its proper place in our consciousness. The blue marble of our world, turning slowly through the night and day, holding upon its surface billions of sleeping minds like your own, each one resting, each one letting go of the day's concerns, in the same way we have let go of the galactic center, allowing ourselves to be held by larger patterns and larger rhythms. Sagittarius A, 26,000 light-years away, will continue its patient existence whether you think of it or not. The starlight that left that region and traveled across the ancient darkness of space to reach your eyes has already completed its journey, and in a few moments, sleep will complete its own long journey to you. The universe is vast, but it is also patient. It has been turning for billions of years, with or without our witness, and it will turn for billions more. Your small place in it, here, on this world, in this moment, is no less real for being infinitely small. The vast and the intimate, the cosmic and the personal, are not separate things at all. They are threads of the same tapestry, and in that understanding, we might find a kind of rest that asks nothing more of us than to let ourselves be held by the weight and wonder of it all.